All right, so let's kind of put this all together. Let's talk about how we can use all these things we've learned about to help us graph polynomial functions. And again, we're assuming we're doing most of this by hand and not using a graphing utility like Desmos or RTI 83 or 84 series, something like that. So the first thing you probably want to do is use the leading coefficient test to determine the graph's end behavior. Once you have that, I would go and find the X intercepts. So that's finding the zeros of the graph. And then you can also figure out the multiplicity there. And the multiplicity, remember, tells you if you're going to cross the axis or if you're just going to touch it and bounce back. Also remember that if your multiplicity is larger, you have a much flatter graph at that X-intercept. It's always good to know the Y-intercept as well. So usually we recommend finding the Y-intercept. And then things from the past, you can also check things like symmetry to see if your graph has any sort of symmetry with the y-axis or origins. We talked about, remember, even and odd functions many videos ago. And then you can also use the turning point information. So if you know the degree, you can find the max number of turning points, which are your max numbers of relative max and mins as well. As I mentioned before, without calculus, it's actually very, very difficult, if not impossible, to get exact locations for turning points. However, you can obtain additional points of the function to estimate how high or low the graph falls by plugging in values, right? So you can plug in different x values if you need to. You can always plug in extra points when graphing. So let's try an example or two and kind of go through some of that procedure here. All right. So the first thing I'm going to look at is I'm going to look at my end behavior. So my highest degree here, remember, this is really where you're focusing. Our degree is 4, which is even. And then my coefficient is 1, my leading coefficient, which is obviously positive. So if you need to, you can go back to an earlier sheet. Let's see if I can still find it here. So it's the second page of our notes, and refer back to how you would do that end behavior. Because n is even, it's going to go the same direction, and because it's positive, both sides are going to go up. So I do know that at the ends of my graph, it's going to look something like this. I'm also going to want to find some x-intercepts here if I can. So I'm going to set that function equal to 0 and solve. Now this is going to factor as x squared minus 1 times x squared minus 1. And I just did this by trial and error. I'm just kind of thinking about my factors for here, my factors for here. Everything was basically 1, so it wasn't too bad of a trial and error problem. And then I can go ahead and find my intercepts. So I have the same equation. So there's actually two things I could do here. One, I could keep factoring each of these and break it down further, or I could solve the two pieces. Both are good techniques, because here I do know how to deal with squares. I've learned how to solve. So I take the square root. Just don't forget you take plus and minus of the square root. So I have two answers, positive 1 and negative 1. And this is going to be the same exact thing. So I don't get any two new answers here. I only have two unique zeros, positive 1 and negative 1. Now, because they're real, they're going to give me the x-intercepts of 1, 0 and negative 1, 0. Okay. Now, another way I can write this if I keep breaking it down further, like I said, now I'm trying to think about multiplicities here, is x squared minus 1 is x plus 1, x minus 1. So each of these does break down a little further. And then if I rewrite this, I see that x plus 1 occurs twice and x minus 1 occurs twice. So both of these solutions each occur 2 times. So they each have multiplicity of 2. So we're going to touch the graph and turn around. We're not going to go through. Remember, when you have even multiplicity, you're not going through the axis, you're going to just kind of touch. And because it's 2, it won't be super flat, but it'll be a little bit flatter than if it was just a multiplicity of 1, for instance. Next, I'd like to find my y-intercept. So you can plug in x equals 0 here. And you get 1. So I have another key point there that I can use. Next, we can try symmetry. So go back to your even and odd function idea here. And remember, you're going to plug in negative x to check for symmetry. So I go to my original function up top here. So this one right here. And I'm going to replace it with negative x. And I simplify. Now, because it's a power of 4, all my negatives will cancel because they cancel in pairs. Same thing here with my square, that will cancel. And I notice that I get the same equation back out. When that happens, we have even functions, and these are symmetric with the y-axis. So I am going to see some symmetry right over that y-axis here. And then the last thing we want to look at is the number of turning points, or max and mins. And that's n minus 1. So my n here was 4. So I can have at most 3 max and mins. So let's go ahead and graph. I probably really shouldn't have put a grid in here because it's, again, you really can't find exact values all the time when doing this. So maybe kind of ignore the numbers and think more just about the general grid here. Let's put in the points that we know first. I know 1 and I know negative 1 on my x-axis. I know 0, 1 here. I know that it's going to be even, so I know that it's going to be symmetric along the y-axis. And I also know my end behavior, so it's going to be going like up this way and up this way. I also know that because of multiplicity of 2 here, that we're going to bounce back. So I'm not going to go through the axes there. So my best guess for the graph is that it's probably going to look like this. I have my 2 end behaviors going in the correct direction. I have my y-intercept and my x-intercepts. I know my x-intercepts are going to bounce back up. They're not going to go through the axis, so they're going to just kind of bounce there. I know I can have at most 3 turning points from this last piece down here. And notice that I have 3. I have a min, and a max. And I do have symmetry with the y-axis. So I have like a general graph here. Again, I don't have exact points along the way. What I could do is I could pick other x values. Maybe I pick x equals 2, see what that value is, x equals 3, and I can pick more and more values. If you go ahead and use your graphing technology, of course, I can do it really fast for you, and you would get a graph that looks like this. Okay, so my graph's a little bit too wide here, must be a little bit faster of an increase. So by having more points, I could do that. Just plug in some more x values to get a little bit more accurate graph there. All right, let's try another one. This is a good time in the video too. If you want to pause the video and try one on your own, go ahead and give that a try. So first, start with your end behavior. Think about your degree here. This one's a little bit harder because it's, well, maybe not harder, but it's in factored form. So here I have an exponent of 2. Here my exponent would be 1. I don't need anything from here because there's no x there. I only want the exponents on things that have variables in them. So my degree here is going to be 3 because 2 plus 1 is 3. This is obviously odd. And then my leading coefficient is still this negative 2. And if you need to, you're going to go back and see if I can find it again, that chart on the first page. So I know I have an odd degree and my leading coefficient is negative. So the left side rises and the right side falls. So this side goes up and this side goes down. right, the next thing I'm going to look for are my x-intercepts. So I'm just following that chart on the page before. And I'm going to set this equal to 0 and solve. Now, the nice thing is when you're in factored form, it does make it easier to solve. I don't need to set the -2 equal to 0 because there's no variable there. If there was a variable, you would do that part too. I just have the x minus 1 and the x plus 2. So here I have x equals 1 and x equals -2. They're both real, so they are going to be x-intercepts. Watch your multiplicities. So this one here has multiplicity 2. And this one here would only have multiplicity 1. Now remember your degree is 3, so this makes sense. So if multiplicity is 2, that means that this solution appears twice. And this is 1, so the solution appears once. So you have 1, 2, 3 solutions, which is what you're supposed to have for degree 3. When you have an even multiplicity, you're going to just touch the axis, right, and turn around. Turn around. And for this one, you'll actually cross the axis when you have a odd multiplicity. Next, we can find our y-intercept. So I plug in 0 for x. So I get -2 times -1 squared times 2. -1 squared is 1. So I end up with a -4 here. Next, I can check for symmetry. So what you want to do is plug in that -x value and see what happens. Oops. Now, I will say this one's kind of hard because you can't really tell right away what's going to happen with it. But it doesn't look like it's going to work very well for us here. So what you could do is you could multiply everything out and see what happens. And same thing for the original, maybe multiply everything out and see if you're getting the original function or something different back out. If we do that, let me do this one quick here. So I would multiply this out. So I have -x minus 1 times -x minus 1. And then I have -x plus 2. So let's see, we'll do this first. So I have 2x plus 2 times -x minus 1. Then I would multiply this next group out, foiling. So I have, let's see, -2x squared minus 2x here minus 2x plus 2. I'm just going to clean this up a little bit before I keep multiplying. And now I'll multiply again. You can see it's kind of a long process. So 2x cubed minus 4x squared. On the next term I do, I would have plus 4x squared minus 8x. And then on the 2, I'd have minus 2x plus 4. So I'm looking at 2x cubed here. These cancel out, minus 8x, oops, minus 2. So that should be minus 10x plus 4. And then what I could do is I could also multiply out the original. So let me pause the video and I'll do that real quick. All right, so I multiplied out the original equation too, just to see what we would get. And when I did that, I do see that my new equation, when I plug in -x and my original don't match, right? They're definitely not the same. So when you have the same equation, it is even. So you have that symmetry with the y-axis. And the other thing you're looking for is that all signs switch. And when that happens, it is odd. So you have that symmetry with the origin. Now, yes, I did get signs switching, but my equations don't match. We need to have all signs switch, but everything else stays the same. So here I'm getting different numbers. I got that 10 in the middle and not the 6. So it's just not quite working. We don't have any sort of symmetry here with the origin or with the y-axis. So in this case, it was a little bit more work to just plug in that negative x because it was hard for me to see with everything already being factored. So what I did was I just multiplied everything out, and then it was easy for me to compare the two equations. Remember, for even equations, you would have the same output. For odd equations, you have the same output, but with different signs. Those are the two things you're looking for. If you get anything else, excuse me, then you're going to have something that's different. So it's not going to have symmetry with the y-axis or with the origin. So we don't have symmetry here. And let's see, the last thing I'm looking for are the turning points. Now our n here we saw was 3, so 3 minus 1 is 2. So you're going to have at most 2 max and mins here. So let's kind of fill in what we have. Let's see. I know my x-intercepts are 1, 0 and negative 2, 0. I know my y-intercept is 0, negative 4, 1, 2, 3, 4. I know that at 1, 0, we have multiplicity 2. So it's just going to touch it, whereas at negative 2, 0, it's going to cross. So this one's actually going to go right through, whereas the other one's only going to touch. And I also know that my graph has to end up here on the left and down here on the right. So if this is only touching, then it must do something like this. And kind of filling this in, it must kind of go down like this. Now I would have at most 2 turning points, we said. So there's 1, 2, 1 min, 1 max. So this is kind of about what my graph would look like. It's a little pointier than it should be. I'm just kind of freehanding and guessing here. So it's a little pointier. And if you graph it, and here you can see they've zoomed out a little bit on the y-axis. That's what your graph is going to look like. So graphing these polynomials, really working with polynomial functions in the real world is actually is very difficult. It really is. So the examples that we focus on are things that you're going to be able to solve and factor. Here again, I'm not worrying so much about all the numbers. I'm just kind of getting that general shape. And then if I need more points, I can plug in more x values. I can plug in x equals 2 or x equals negative 5, x equals 10, whatever I want to have a couple more values to have more concrete numbers on my grid. Here I was just kind of just doing a quick rough graph. But again, realistically in the real world, we're probably using technology to help us with a lot of these examples because they can get really complicated very quickly. If you have a degree that is large, let's say you have an exponent of degree 10, you could have up to 9 turning points. That would be 9 max and mins. That's a lot. So there's a lot of different things that can go on, a lot of different bumps and changes. And you can see that, you know, the difficulty level definitely does increase as you get into higher degrees.